Hi there, I'm David, and I'm going to talk about electrochemical cells. But what's an electrochemical cell, you ask? An electrochemical cell is a device capable of generating electrical energy with chemical reactions. It's also capable of facilitating chemical reactions with the introduction of electrical energy. But first, let's define some key concepts before we get into electrochemical cells. Oxidation states is one of the key technical aspects of electrochemical cells. The oxidation state of a substance is a quantitative and qualitative measure of how much it loses electrons or gains them during a redox reaction. There are 8 steps in assigning the oxidation state of a substance, and these will be discussed now. The first rule is that free non-bonding atoms or molecules have zero oxidation state. The second rule is that compounds have a net charge of zero, as the oxidation states of the component atoms or ions balance out each other. The third rule is that ions have an oxidation state equal to their charge. The fourth rule, the sum of the oxidation states in a polyatomic ion must be equal to the charge of their ion. The fifth rule is that hydrogen takes either +1 or -1 as its oxidation state. It takes +1 when bonding with nonmetals and -1 when bonding with metals. The sixth rule is that fluorine takes -1 as its oxidation state in all cases. The seventh rule is that oxygen, the second most electronegative element, takes -2 as its most common oxidation state. It, however, takes -1 when it's in peroxide form or -1/2 when in superoxide form. The eighth rule is that members of family 1A have an oxidation state of +1, members of 2A +2, and members of 3A +3. On the other hand, family members of 5A have -3, 6A -2, and 7A -1. Now that we've discussed oxidation states, we must now discuss the primary mechanism which drives electrochemical cells. Before that, however, we must familiarize ourselves with some certain terms. The anode is the terminal of the battery where the oxidation reactions happen, and the cathode is where reduction reactions happen. What we call the oxidation reaction and the reduction reaction on their own are half reactions. Inside this battery, they occur simultaneously in the half cells. In one of the half cells, there is a reducing agent, and in the other, there is an oxidizing agent. They're both dissolved in a basic media because 9-volt batteries are alkaline batteries. So what happens here is that a cellulose barrier protects both the half reactions from interacting with each other to achieve equilibria. If equilibria is spontaneously achieved, all the energy will be lost and nothing will be harnessed. So what happens here is that the battery takes advantage of this by separating the half reaction. The combination of these factors results in what we call redox reactions. The redox reaction derives its name from its half reactions, namely the reduction reaction and the oxidation reaction. The oxidation reaction means there is a loss of electrons, and in the reduction reaction, there is a gain of electrons. A handy acronym for this is the oil rig acronym, or the Leo de Lion says GER acronym. The oil rig stands for oxidation is for loss, and the reduction is for gain. While Leo de Lion says GER stands for loss of electrons, oxidation, and gain of electrons, reduction. We call the substance that is reduced as the oxidizing agent and the substance that is oxidized as the reducing agent. Now let's go back to the redox reaction. The redox reaction will not occur if the half reactions don't occur simultaneously. This means that an oxidation will not occur if the reduction reaction does not occur as well. Most of these reactions, however, redox reactions, are spontaneous. Therefore, most electrochemical cells, such as this one, are voltaic cells. As I've said before, a majority of redox reactions are spontaneous by nature. This means that a lot of electrochemical cells are fueled by spontaneous redox reactions. This means that a lot of them are galvanic or voltaic in nature. This is an example of a voltaic battery. This is the Daniell cell. A good example of a voltaic cell is the Daniell cell. It involves zinc and copper ions dissolved in sulfate solution. In the anode, oxidation of zinc occurs. The zinc electrode slowly dissolves and produces zinc ions which enter into the sulfate solution. In the cathode, reduction of copper occurs. This results in the deposition of copper around the electrode. In this cell, the two half cells are connected by a wire and the salt bridge. The wire allows for electron transfer while the salt bridge allows for ion transfer. The salt bridge prevents a charge from building up on either side, which will then hinder the system. The electrolytic cell requires the introduction of electrical energy from an external source in order for the reaction to proceed. This process is non-spontaneous. This process also is far too complicated, and therefore we prefer to stick with voltaic cells. Now that we're familiar with the electrochemical cells and the mechanisms that make it run, we're going to discuss the maximum voltage one can produce in standard conditions. We first introduce the E0 red. It's also known as the standard reduction potential. The standard reduction potential is a value that you compare to the SHE. The SHE is the standard hydrogen electrode which has a potential of 0, making all comparisons to such absolute. Now that we're familiar with the E0 reduction, I will now introduce the E0 cell. The E0 cell is equivalent to the E0 of the cathode less the E0 of the anode. One, however, must be careful with the E0 of the anode, as if it has a lower SRP, it will be flipped. It will become the negative of its SRP, or its E0 reduction. This is the end of our lesson on electrochemical cells. Thanks for listening.